Already. Let's see if this is working. Everybody sees what I've got here. You see the mouse cursor, the pointer? All right, very good. So thanks for the invitation. It's a pleasure to give a talk on the gauge theory virtual. I guess as I warned Dave, there isn't any gauge theory in this talk. So well, at least not in the foreground, maybe I guess in the background a little bit, but this is just a talk in essentially symplectic and contact topology. And it's all joint work with Boulant Tosin at Alabama. So, great. So the question I wanted to talk about was, well, about contact topology. Sorry, I'm distracted by my setup here. Let's see if I can. Okay. There we go. Okay. Right. Okay. So contact topology. I guess most people maybe everybody knows the background here, but we're talking about contact three manifolds. That's the three manifold with a certain kind of two-plane field given as a kernel of a one form, satisfying this non-degeneracy condition.
So Tom, I'll interrupt.
Yeah.
Ian was asking if you could make it full screen.
I can give it a shot. Every time I
think it's fairly readable if it's not.
so it's full screen for me. Does it look the same for you, or is it okay?
It's good.
Is it better? Or like I said, it's full screen for me, but let me know if there's anything else I can do. Okay, right. So contact structures on three manifolds. So one basic fact is that any three manifold has contact structures. And just like the theorem that says that a three manifold can be attained by surgery and a link, there's an analogous theorem about obtaining a contact three manifold by surgery on a Legendrian link from the standard contact structure on S3. So I'll review this a little bit. But the question we're going to think about is what properties of the contact manifold you can read off from the surgery description. So the properties I'm talking about, for example, are essentially fillability properties. So Stein filling is maybe the most technical, the strongest condition. That would mean that you're the boundary of some complex surface that has a certain kind of Morse function where your boundary three manifold is a regular level set. So the only example we'll really need or think about explicitly is the three sphere with that Morse function. So the three sphere is Stein filled by the four ball. But more generally, you could talk about a strong symplectic filling. So that's a compact symplectic four manifold that has a Liouville field near its boundary. And if I don't really need that concept, so I'm not going to define it. The only kind of version of fillability that we're actually going to focus on is weakly fillable. So that means that your three manifold is a boundary of a symplectic four manifold with its symplectic form, so non-degenerate two form. And the condition of weak filling is that restricting the two form to the plane field, the contact planes, which are oriented, should be non-degenerate, and it should be an area form on the planes. So all of these properties imply tightness for the contact structure, and each one is sort of weaker than the previous by a strict sense. Okay, so those are the sort of the fillability properties of what we're wondering about in terms of contact surgery. So how does contact surgery work? Well, one way to talk about it is you start with a Legendrian knot. So Legendrian means that your knot is everywhere tangent to the contact planes. And if that happens, then the knot is framed just looking at the normal direction to the knot in the contact planes. So that's gives you what's called the contact framing, or sometimes the Thurston-Benneken framing. So let's, if you're going to do surgery, what do? You sort of trivialize the normal bundle and you take or trivialize the neighborhood. So you take a longitude, and the standard thing to do in this situation is you take one corresponding to the framing that we just got from the contact structure. And you pick your irrational number that's going to be your surgery coefficient, and you remove the neighborhood of the knot or replace it with another solid torus. So that the boundary of the disk is glued to P meridians and Q longitudes, where Q or lambda is this longitude. Now, the point is that if you're talking about a Legendre knot in a contact manifold, you are choosing your neighborhoods appropriately, then you can always, if you restrict the contact structure to the complement and do the surgery, then you can always extend it back over the new solid torus in some way. What you get is called the contact R surgery. R is a surgery coefficient. In general, there'll be some choices involved there, which are pretty well understood. And for our purposes, there's sort of a canonical choice. So I'm not going to really talk about it. It's sort of a natural choice here that we're always making. And maybe the only little caveat to bear in mind is that when you do a contact surgery, you measure the surgery coefficient with respect to the contact framing. And if you're doing smooth topology, you tend to measure the surgery coefficient with respect to the no homologous framing. So there's a difference there, and that difference is a Thurston-Benneken number. So there'll be some back and forth about contact surgery versus smooth surgery, but I'll try not to fuss too much about that. Okay, so there we are. So as far as a little bit of extra background, we were thinking about when surgery preserves these fillability properties. And if you're doing negative contact surgery, then essentially all of those properties that I listed are preserved. If it's fillable in any way, then the result of surgery for a negative surgery coefficient is also fillable. It follows from work of Eliashberg. And surgery with a negative coefficient also preserves tightness by theorem of Andy Wands. If you do contact zero surgery, I mean, you can if you want, you always get something over twisted, which is never fillable. So let's not worry about that. So let's think about positive surgery. And the point is that sort of anything can happen in principle, because there's a theorem that says that every contact manifold can be obtained by surgery on some link in the standard 3 sphere. And in fact, if you want, you can make all the surgery coefficients negative except possibly one of them. So as far as fillability, the whole question boils down to, if you do a positive surgery on a knot, is the result fillable or not? And sort of that's going to, in principle, sort of resolve the question, I guess. So right, the point is that sometimes that's not going to be fillable because there are such things as non-fillable contact structures. Okay, anyway. Okay. So that's our basic question. If you have a contact manifold and Legendrian in it, when is it the case that that some positive surgery with positive contact surgery coefficient becomes a fillable contact structure? And so I'm just going to tell you the answer, and then we'll kind of start unpacking it sort of for the rest of the talk. So the theorem says that, well, we're only going to consider integer surgeries. So there's an integer with the property that the positive contact integer surgery is fillable by some symplectic manifold Z prime, if and only if, well, first of all, the 3 manifold you started with had to be fillable. And moreover, this is sort of the interesting part, I guess. The surgery, you have a fillable positive surgery only if you have some filling of your original manifold that contains a symplectic disk whose boundary is the knot you started with. Strictly, it's a transverse push-off, but again, some of these details I'll ignore a little bit. So some filling of your 3 manifold Y, you had to have some filling in which your knot is sort of symplectically sliced, I guess. That's what the theorem says. And moreover, it turns out that your surgery has a weak filling in such a way that, in fact, your slice disk for the original knot, you can always choose it so that the complement of that slice disk in a suitable, suitable neighborhood of the slice disk gives rise to the filling for your surgery. So every filling of the surgery is obtained by this as a complement of the neighborhood of the slice disk. So I'm going to state that again in its own theorem. So there it is. If you have a symplectic disk and properly embedded in a symplectic manifold boundary, it's kind of weak filling something at the boundary, then you can remove a neighborhood of that disk, and obtain a weak filling of some contact manifold, which is obtained by positive contact surgery along the boundary of the disk. Okay, so that's sort of the general statement here. And like I said, I'm going to maybe postpone any talk about the proof, which maybe we'll have time for in we won't say very much about it in any case, but I'm going to kind of focus on knots in S3 just because it becomes interesting to see how much you can say about knots that have this property. But for now, are there any questions about the general statement?
So do
Okay.
you know
Yeah, I'll ask, in your statement, are you saying that you'll then get all positive surgeries or just there is one if you have this disc?
Right, that's a good question. So the theorem says that there is some positive surgery that's fillable if and only if these conditions happen. Then the question becomes which surgery, and we'll talk about that quite a bit as we go along. So I'll say quite a bit more about that question as we go. Anubhav, was that your question, or do you have something else?
Yeah, so I was also kind of curious, like what kind of integer n? Like, is there exist infinitely many, or like everything bigger than or smaller than, you can say more?
That's right. It's going to be a half infinite interval. I'm going to state that precisely in a few minutes. Yeah. Okay. Well, so let's focus on knots in the three sphere. So, the theorem says that if you're looking for a knot with a fillable positive surgery, it should be bounding a symplectic disk and some symplectic filling of the three sphere. Well, so you want to know what the fillings of the three sphere are, and they've luckily been classified. They're all blowups of the four ball. So what we're looking for, if you have a Legendre, you want to know if it bounds a symplectic disk in a blowup of the four ball. And if you find that, then you've found the filling. Anytime you find such a disk bounding K in some blowup, you can scoop it out of that blowup of the four ball, and what's left over is a filling of the surgery, of some surgery, and every filling can be obtained that way from some symplectic disk. Okay, so we haven't said much more than what we said already. But here's an example in any case to get us started. If you look at the knot 820, there's a picture of it in no particular position except the one that knot info gives you. And I think maybe we need the mirror of this picture, but I'm not quite sure. So the point is that 820 is a slice knot. In fact, it bounds an embedded disk in the four ball itself, embedded symplectic disk. In other words, you didn't need any blowups at all. So you could scoop that symplectic disk out of the four ball itself, and the result, part of the theorem is that the complement of that disk is a symplectic filling of its boundary, which, of course, if you scoop a disk out of the four ball, their boundary is zero surgery on the knot you started with. In this case, you have, it turns out you can find without much trouble a Legendrian representative of this knot having Thurston-Benneken framing -2, and so the difference between that and zero surgery is +2. So that means you're finding a filling of contact +2 surgery. So you might wonder how you know that you have a symplectic disk, and the buzzword there is that the knot is quasi-positive. We'll talk more about that in a little while. Okay, so back to the general situation, or at least general in S3, we said that any filling of a positive surgery on a knot in S3 is obtained by scooping a disk out of a connected blowup of the four ball. And so since the blowup of the four ball has negative definite intersection form, if you cut a disk out of it, then what's left still has negative definite intersection form. So in particular, like, there's a topological consequence that the smooth surgery you do on the 3 manifold has to be smoothly the boundary of a negative definite 4 manifold. And that's not always, it's not obvious that that's just going to happen automatically. So that's actually a non-trivial constraint that, if you have a surgery on your knot that doesn't bound negative definite, then that surgery can't correspond to a fillable contact surgery. Okay, so let's think a little more about how to find fillables surgeries. So for one thing, if you have a disk in the blowup of the four ball, it's symplectic. You can do some symplectic perturbations and stuff. And do symplectic blowdowns, and your disk in general, you blow it down. If it intersects in exceptional spheres, you'll introduce some singularities, but whatever, you get some singular symplectic disk in the four ball itself. it's still bounding your knot. In fact, if you want, you can perturb everything so that that blown down disk is immersed and it just has double point singularities, and you can force them all to be positive double points. So another way to say the main result for the case of a knot in the 3 sphere is that you have a fillable positive surgery if and only if it bounds some immersed symplectic disk in the 4-ball that has only positive double point singularities. So for example, suppose your knot happens to be a closure of a positive braid. And I mean, again, there's some words you should mumble about keeping track of whether it's Legendrian or transverse or, okay. Think of your knot as a positive braid. Well, there's a nice algorithm that was written down by Boileau and Weber some time ago that says you start with your positive braid diagram, then you can find a collection of crossings in that diagram with the property that if you change the crossings, so changing positive crossings, you end up with the braid whose closure is unknotted and has n-1 crossings. So you change some positive crossings of the braid, you get to an unknotted braid closure that has exactly n-1 crossings. So the point is that if you think about, changing crossings as some sort of singular isotopy, then you kind of look at the trace of that, that you're not thinking of your knot as transverse to start with. When you do this isotopy, it sweeps out a symplectic surface, and then changing a positive crossing means that that surface has a self-intersection, and it's a positive because you've changed a positive crossing. So doing these crossing changes sweeps out a symplectic annulus with positive double points in it. Then you're at this unknotted braid closure, and if you kind of count things up, then that's going to be some sort of standard unknot, at least up to transverse isotopy, and so that'll bound an embedded symplectic disk itself. So you attach the singular annulus that you swept out at first with this symplectic disk, then you get a symplectic disk immersed in the 4-ball, bounding your positive braid, and so the theorem says you have a fillable positive surgery. Okay, so corollary is that if you have positive braid, then every positive braid emits some fillable positive contact surgery. Okay, so that's one example. Here's another one. Suppose you have a knot that emits a lens space surgery, so a positive surgery that's a lens space. Though I claim that you're going to have a fillable positive surgery as well, a contact surgery. In fact, the contact surgery that sort of corresponds to this smooth surgery is going to give you a fillable contact structure. So what's the idea? Well, let's just think about, so assemble some stuff from the literature. It's a theorem that, if you're going to have a P surgery, which is a lens space, then your surgery coefficient has to be sort of sufficiently large. In fact, the surgery coefficient has to be at least twice the genus. 3 genus, that's the theorem of Josh Green. And that means, the Bendekin inequality says that Thurston Bendekin is less than 2G3, so that means that if you do a contact surgery to get this, then the contact coefficient is positive because you have to go above TB to get to the lens space. On the other hand, again, there's this word quasi-positive again, but it turns out that your knot has a representative satisfying this equation here. The TB plus rotation is 2G minus 1. But the point of that is that if you do contact surgery with this contact surgery coefficient that you needed, you get a tight contact structure. So this is because the Hegard-Fleur contact invariant is non-trivial. That follows from work of Gola that Boulant and I generalized a little bit as well. Okay, and so that means that when you do the contact surgery that gives you a lens space, you get a tight contact structure on the lens space. But every tight contact structure in a lens space is fillable. So you got a fillable surgery. Yay, okay, so positive braids have fillable surgeries, and lens space knots have fillable positive surgeries. Okay, there's various other constructions that we could talk about, but maybe I'll come back to the sort of other questions and use what we've just done as sort of illustrations a little later. So there's a question before about what surgery coefficient you get as fillable. Okay, so it doesn't specify, the theorem a priori doesn't tell you which surgery. So here's how you can, one way to think about how to figure out the surgery coefficient. Fillable surgery means you bound this disk in the blow up of the foreball. And such a disk has some kind of, well, relative, whatever, its boundaries S3, so it has some kind of homology class, a linear combination of the exceptional curves, generators of the blowups, okay? And you know that the filling is the complement of the neighborhood of that disk. So that means that the boundary of the complement of the disk is some surgery on K, and what is P in this language? Well, it's just like you attach, you know, you're coming in from the boundary and you're scooping on a disk. That's sort of the same thing as if you had attached a boundary to the 3 sphere along K, except that you're looking at the boundary from the other side. So the surgery coefficient you're using is the self-intersection of the 2 handle, which in this case is the disk, except that, so that's this number, the self-intersection of the disk. You have to reverse the orientation because you're looking at it from the other side. So the surgery coefficient you get is the opposite of the self-intersection of this class, and the EJs have square minus 1, so you just get the sum of the squares. We okay? Questions about this? Okay. One kind of side note is that this number is non-negative. So it turns out this is the smooth coefficient, which a priori, if you're saying you're doing fillable positive contact surgery, the smooth coefficient operator doesn't have to be positive, but this says that actually it is, which is actually sort of, it's going to be true in general, but not just for S3, but here's a direct argument for S3. Okay, so that means your smooth coefficient is given by this formula. So one thing you can observe is that as soon as you find a disk in the foreball with a blown up foreball, you could blow it up again if you want. You could blow up that disk again at some smooth point, and you get another smooth disk bounding the same knot and one further blow up of the foreball, and the self-intersection of the disk decreases by 1 when you do that. That means the surgery coefficient increases by 1 because you're supposed to negate the self-intersection. So that means when you scoop this symplectic disk out of the larger blowups, you get a filling of a next larger surgery coefficient. So that's this corollary, which is I sort of said out loud a little while ago, that the set of smooth surgery coefficients that correspond to fillable positive contact surgery, I mean, it might not have any, so it could be empty, but if it's not empty, then it's a half infinite interval of this form, starting at some number P naught or something. Okay, so that P naught becomes the interesting question. What's the smallest fillable surgery coefficient for a given knot? Okay, so that's some invariant of a Legendrian. So that, well, okay, if it's defined, you're going to make it defined for all Legendrians. Let's set mu of K to be infinity if there's no fillable surgery. Otherwise, it's this smallest fillable surgery coefficient.
Can I ask you another question? I'm a little confused. So your statement saying it's an if and only if condition. So does it imply that every non-loose knot has no fillable, like if you do a surgery on a non-loose knot, that has no fillable contact structure?
That's right. A positive contact surgery on that can't be fillable because you have to start with a fillable structure.
But if you start with like a non-loose torus knot, some surgery gives you lens space, right?
Right, but I don't think you'll ever be able to prove that that's tight, or else it might be a negative contact surgery. You can cause an over-twisted guy to become tight or fillable by doing negative contact surgery. But what we're saying is if you're going to do positive contact surgery, the only way to get something fillable is if you're in particular, the 3 manifold you started with had to be fillable.
I see. Okay. That's interesting. Okay. I'll think more. Thank you.
Okay. Okay. So let's see. What can we say about this mu, this minimal fillable surgery coefficient? Well, so here's a lemma. I claim that mu is no more than 4 times the slice genus of your knot. Well, okay, so it's not too bad. So if you have have a fillable surgery at all, then there's some symplectic disk immersed in the four-ball, as we observed before, having some number of double points by sort of making it generic. So what do? Let's smooth the double points. So you can do that symplectically. And then you get an embedded symplectic surface bounding or not. And it has genus. Every time you smooth a normal crossing, you just introduce, kind of cut out the double point and glue in an annulus. You increase the genus by 1 every time you do that. So you get a genus M surface, where M was the number of double points you had to begin with. But you know that if you bound a symplectic surface of some genus, then that genus is actually the minimum overall of the genus of any even smooth surface bounding or not. So that M has got to be the four-ball genus. On the other hand, starting with the immersed disk, you can blow all of the double points up, and that gives you a disk inside the M-fold blow up of the four-ball. And since you're blowing up double points, the coefficients of the exceptional curves you get are all 2. These are kind of double points. So that means the self-intersection is 4M, and M is 4G star. So that means 4G star surgery. This number is the surgery coefficient, right? So the 4G star surgery is fillable. So that means you had to have gotten, if you have a fillable surgery at all, you have to find one by the time you reach 4G star surgery. It's kind of 4 times the slice genus surgery is always enough to hit your fillable surgery. Okay, but the point of that, or one kind of consequence of that proof, is the following. So, or maybe one kind of direction starting from those ideas is that if you have a fillable surgery, then you just notice that you bound an immersed disk, and that if you want, you can make all the singularities to be transverse double points, and that in that case, it would have to be G star of them, the slice genus number of them. Okay, so that means your mod bounds a fairly special kind of immersed disk in the four-ball. So there's an invariant of just smooth knots, which is called the clasp number, which is the minimum number of double points in any immersed disk in the four-ball that bounds your knot. Not symplectic, not positive or negative, whatever, just however many double points you need in order to find an immersed disk with boundary K. And anytime you have an immersed disk like that, you could smooth it by adding genus, and you get a surface of C number of genera, genus C, and so that means that C has to be at least the slice genus. And what we've shown is that if you have a fillable surgery, then these numbers have to be equal, but on the other hand, in general, the class number can be much larger than the slice genus. So this was an object of recent study independently by a couple of people, Dami Scudugo and Juhas and Zemke, kind of independently gave different kinds of examples showing that this class number can be arbitrarily larger than the four-ball genus. But the point is that if you have fillable surgery, that doesn't happen, and the class number and the four-ball genus had to be the same. Well, so for example, if you have a lens-based surgery, we already showed that it has a fillable surgery, so the class number has to be the four-ball genus. So this is just a purely topological statement now. It doesn't depend on any symplectic geometry. All it comes from our symplectic considerations. But the point is that we don't know any other way to prove this statement. I mean, maybe other people knew this already. It's certainly known in all sort of concrete examples of knots with lens-based surgeries. But this is a general statement that we don't know another way to prove, and so that's kind of find that interesting. And if you're interested in sort of generalizing this, you could ask whether the same statement holds, or even whether the existence of a fillable positive surgery holds if you, instead of a lens space knot, you have a general L space knot. So we don't know. I mean, we have various constructions for knots with fillable positive surgeries, and you can get lots of L space knots that way, but we don't have a general proof or general answer to this question. Okay, let's just throw in another example for fun. Here's another picture. I think this is the correct chirality of this diagram. Anyway, the point is, but this diagram has all positive crossings. So that's maybe you could consider that to be promising news if you're looking for fillable surgeries. That means, for example, it's strongly quasi-positive, which tells you that it bounds an embedded symplectic surface in the four-ball. Again, we'll come back to quasi-positive a little bit if that's not something you're familiar with. Anyway, it bounds an embedded symplectic surface. In fact, it bounds a Lagrangian surface. This is something that people have constructed explicitly in the four-ball. Moreover, it has the property that you can find Legendrian representative and such that more or less every positive contact surgery is tight, has non-zero contact class, for example. But its class number is 2. The kind of the interest in recent years, people have been sort of poking around at this knot in recent years because of this fact that the class number is known to be 2, but its slice genus is 1. So there's none of these tight contact structures can be fillable. In fact, this knot doesn't have any fillable positive surgeries. Okay, well, that's fine. Let's come back to the question of which surgery coefficient is fillable. So we can get a little more detailed. Before we saw that it was enough to take 4 times the slice genus as your smooth surgery coefficient. If you had a fillable surgery, then that one would be fillable. But maybe you can find a fillable surgery before you get to 4G star. Okay, well, suppose you have a fillable surgery and that corresponds to some disk. It's like that filling is like the complement of this disk. The disk is a linear combination of the exceptional curves and the surgery coefficients and some of the squares of the coefficients. So one thing you can do, well, I mean, before we kind of took the smooth disk and blew it up, but you can, in principle, at least if you have a disk that intersects one of the exceptional curves in a single point, you can blow it back down, and that'll decrease the surgery coefficient by 1. And then there's a version of positivity of intersections here that actually says that these coefficients, since the e's and the delta are both symplectic, I mean, you have to argue why it's, I mean, in general, symplectic intersections don't have to be positive, but in this case, you can argue that you can make them all positive. So these NJs are actually, you can take them to be the geometric intersection number of your disk with E, at least if it's transverse. The point is that there's some version of positivity of intersections. And so you can do this blowdown trick exactly when you have a surgery coefficient or a coefficient of one of these exceptional curves being 1. Okay, well, that's not so, I mean, there's no reason to suppose you would have that, I suppose. So if the coefficient of E is bigger than 1, so you have a disk that kind of crosses through exceptional sphere kind of algebraically more than once, it might be tangent in some degenerate way, but you could always perturb symplectically, and then you arrange it intersects exactly NJ points. And if you do that, you can blow it down. And then the point is that the blowdown is now some easy singularity. It's just an ordinary multiple point, order NJ. And after that, you can perturb the multiple point to become a whole bunch of double points. You do that, you smooth all the double points, and you count how many you had, and like each NJ multiple point gives you this many double points after you kind of smooth it out. So this gives you, and you know that after you smooth everything, you have to have a surface of the genus equal to the four-ball genus. And so you have this formula for the four-ball genus in terms of these coefficients. So there's a recopy of that formula right here. Maybe one observation is that this number obviously is obviously less than the sum of the squares, unless it happens that all the n's are 0, which is not super interesting because then you're sliced in the four-ball. You didn't need any blow-ups at all. And so then the four-ball genus is 0. So what I'm telling you is that the coefficient you need, which is the sum of the squares, is always bigger than twice the four-ball genus. I mean, it could be equal if the slice genus, if it's not a slice, but otherwise it's strictly bigger, and no more than 4 times the slice genus. So this is sort of a basic bound on this smooth surgery coefficient. And it turns out, well, it can. So this first inequality is basically always strict. The second one may or may not be strict. I mean, you can realize it in some cases, and in other cases, there's a strict inequality there. In fact, this number mu is not an easy function of. It's not determined by the genus of your knot or some basic quantity like that. We'll maybe see that by the end, but anyhow. Here's another example. So there's our Finishel Stern knot, a -237 pretzel knot. You look up interesting facts about this knot, and you learn that it has slice genus 5. And the reason it's called a Finishel Stern knot is that it was observed first presumably first, as far as I know, it was first observed by Finishel and Stern, that if you do +18 smooth surgery on this knot, then you get a lens space. Okay, so that means that it has a fillable positive surgery, and the smooth coefficient, you could take the smooth coefficient to be 18. That's already less than 4 times the slice genus. But you can still ask what the smallest fillable positive surgery is. So I claim that 17 surgery is also fillable on this guy. So it's just a fun game. So, how do you show that if you know 18 surgery is fillable, how do you study 17 surgery? Well, 18 surgery means you can find a disk and some blow up with linear combination of exceptional spheres, surgery coefficient 18, so the sum of the squares is 18. If none of the coefficients are 1, I mean, if there's a coefficient 1, then you're done because you can blow down and get to 17. So suppose none of them are 1. The only way you can sum squares and get to 18, where you're not allowed to use 1, is where you take 3 squared plus 3 squared. But you plug into the genus formula, you find slice genus 6, but it isn't slice genus 6, so too bad. So one of these ends has to be 1, and you can blow it down to get 17, a filling of 17 surgery. All right, well, so how far can you go? Well, there's a fact that one can pull out of a hat, I suppose. It's independently proved, I believe, by Amenkalote Bulantosen and by Liam Yu, which is that if you do 15 surgery on that particular pretzel knot, then the resulting 3-manifold is not the boundary of something negative definite. This is kind of coming from lattice embeddings and Donaldson theorem and stuff like that. Okay, but we know that if you have fillable positive surgery, then that thing has to be the boundary of something negative definite. So then the smallest coefficient of fillable surgery is bigger than 15 and no more than 17. Well, so I claim you can't fill 16 surgery. So what's the game? You do the same thing. Suppose you have a disk, but it's going to give you filling of 16 surgery. So sum of the squares is 16. Again, one of the ends can't be 1 because you could blow it down and get a filling of 15 surgery, and there ain't 1. So what else can you have? Sum of the squares is 16. You can either have 4 2s, but you plug in the genus formula, that gives you genus 4, or you could have a single 4, that gives genus 6. So nope, it doesn't work. So that means you can't have 16 surgery fillable at all. So this should say 17. Sorry, we just proved that 16 surgery is not fillable, right? So mu of the pretzel knot is 17. Okay, fun. All right, so let's come back to this quasi-positive thing. You can actually kind of say, you don't just have to play little games like this, one knot at a time. You can say what kind of knots you get here. So here's kind of the official definition of quasi-positive. So it was a braid. It's a definition for a braid. A braid is quasi-positive if you can write it as a product of conjugates of positive powers of the standard generators in the braid group. And the kind of interest for our purposes in this definition is that being quasi-positive, or really being the closure of a quasi-positive braid, is the same thing as being the boundary of a symplectic surface embedded in the foreball. Not a disk, right? But just some symplectic surface embedded in the foreball. That happens if and only if your knot is quasi-positive. Okay, so we already saw, okay, having a fillable surgery means you bound an immersed disk in the foreball with positive double points, which you can always smooth to give you a symplectic surface. So if you have a fillable surgery, you bound a symplectic surface, so you're quasi-positive. So that's a necessary condition, but you can do better than that. The fact that that surface had to come from an immersed disk means you can kind of play the following game. So if you just take a standard Artin generator and conjugate it, the terminology for that is sometimes people call that a positive band. There are geometric reasons for that, but we can skip that. If you conjugate the square of a generator, you call it a node. And the point is that bands correspond to sort of one handles in your slice surface, and nodes correspond to transverse self-intersections, which are positive because you're talking about a positive braid generator. Okay, and in particular, right, if you write a braid as like a product of expressions like this, you can sort of pretty much see a symplectic surface that it bounds. And this, with this many, however many nodes there are, tells you how many double points there are on the surface. And the numbers of disks and one handles tells you the Euler characteristic of the surface. So in other words, the genus. And the number of disks in your handle decomposition of the surface is the same as the number of strands of the braid. Okay, so what's the point? The point is you can use these ideas to say exactly when you have a fillable surgery. It happens exactly when you're quasi-positive. We knew that was necessary, but this braid has to be special if it's going to come from an immersed disk. So it has to be quasi-positive in such a way that if it has n strands, that gives you n disks in your handle decomposition. They each have to be connected up because we're talking about a connected surface. So there has to be n-1 bands, but you don't want any more one handles in the surface because then you would introduce genus. So any remaining terms in this quasi-positive expression have to be nodes. So you have n-1 bands, and the rest of whatever your braid looks like has to come with squares of generators. So here's an example. If you, again, just poke around on not info, and you look at the not 10-142, not info tells you that it's quasi-positive, and it looks like this expression, a quasi-positive expression for it is this one. So like in general, quasi-positive means product of conjugates. Everything here is sort of unconjugated or trivially conjugated, except this expression in parentheses. There's just the one. So there, in particular, there's like one band for each term here. There's 3 bands there. One more makes 4, 5, 6, 7, 8, 9 bands. And what you're looking for in terms of nodes are square generators. So there's one and there's one, but that's still got 5 bands left over. So we need only 3 because we're in the four-stranded braid group. Oops. So, but in this case, it turns out you can just fuss around with it. So you can replace this sigma 2 using the braid relation, and you just muck around, and you can make this conjugation bit a little more complicated, but you don't really care. It's still just a band. It just turns out to pop out a sigma 1 on this side, absorb 1 from that side, but luckily you had an extra. So now there are 3 nodes and 3 bands left over. So this big conjugate thing is a single band, and each of those sigma 2 and sigma 3 is a single band. So there you go. It's only got 3 bands. So this basically describes for you an immersed disk bounded by that knot. So you have a fillable surgery. Okay, and once you sort of understand how to play this game, it's very easy, and you can just go through the table. So if you look at, you ask not info to tell you the quasi-positive knots in their braid expressions, and either they violate this obstruction, which luckily not info tells you what the class number is for knots up to 10 crossings, which is thanks to work of Owens and Strelay for the most part. And either they violate this condition, in which case they don't have a fillable surgery, or you can muss around like I just did and get a suitable braid expression and get a fillable surgery. And it turns out that like majority of quasi-positive knots in this range have fillable positive surgery. I don't know if you should consider that to be surprising or not. I mean, once you say quasi-positive, you're sort of close, but I don't know. There it is. So there's some additional questions we can think about. I already mentioned one, which is whether an L-space knot always has a fillable positive contact surgery. For example, like here's a particular case. As far as we understand, we haven't worked too hard on it, but as far as we understand at the moment, if you take the right-handed trefoil and do the 2-3 cable, what the result is an L-space knot. It has an L-space surgery, but it does not have a lens space surgery, and you can't express it as a positive braid. So previous sort of general theorems don't work to tell you it has a fillable surgery. So, I mean, that's something to play with. What about an example where it has a fillable surgery, but but you know, but this bounding negative definite criterion isn't sharp. So maybe I'll give, if there's time. Do I go till 2:30 or do I stop in like 3 minutes? Does it matter?
You can go a little bit longer than 3 minutes, but
Okay. Well, I don't have a whole lot more to say, but
yeah.
Anyway, the examples that we know, where we know sort of both the minimal surgery coefficient that's fillable and the minimal coefficient for which you bound a negative definite, those numbers are the same, but we don't quite know the minimal surgery coefficient that bounds negative definite for this pretzel knot. We know that 16 surgery is not fillable, but it's unknown whether 16 surgery bounds negative definite. So it might be interesting to settle a question on that example, at least. And there's also, the fact that up to 10 crossings, at least, it was enough to know this class number constraint if you were going to obstruct fillable positive surgery. Everybody that satisfied that constraint had a fillable surgery. So presumably that's not sufficient. If you know that you bound some smooth disk, even with only positive double points and G star many of them, presumably, and you maybe know you're quasi-positive, presumably that's still not enough to say that you have a symplectic disk with only positive double points, but we haven't got an example of that yet. So in the last couple minutes, maybe here's just some sketch of how you prove this stuff. Actually, maybe I'm gonna do this in the other order. I'm gonna go to my examples. One more example. So look at a Torus knot. It has a fillable surgery for like several reasons now. It has a lens space surgery. It's also a positive braid. Okay, fine. So what's the smallest coefficient that's fillable? Well, so the answer is the following. Well, here's the starting point to the answer. Suppose you do a continued fraction of P over Q, but I'm going to do the positive continued fraction because it turns out that's what we need. So it's not like what you usually do if you're thinking about curvature calculus, but okay, that's what we need here. So we're doing a positive continued fraction expansion. And then Owens quite some time ago determined exactly when a surgery along the Torus knot bounds some negative definite form manifold. It happens exactly when your surgery coefficient is at least this number, M, and that number is PQ minus this continued fraction. So this continued fraction is basically the one you started with backwards, except that you might stop at 2. Instead of going from n down to 1, you might go to n down to 2. If you have even number of terms in this expansion, you go from n down to 2. If you have odd number, you go from n down to 1. Okay, so this is, in general, this is a rational number, not an integer. And so that's sort of curious that, surgery on a torus knot bounds negative definite. The first time it does that is some rational non-integer number. I mean, I don't know if that's surprising or not, but there it is. We were only talking about integer contact surgeries. So whatever contact surgery you're looking at that's supposed to be fillable, whatever number that is, it has to be at least the ceiling of this number. Okay, but it turns out that if you kind of just do some basic geometry and you think about what your torus knot is like the link of a singularity in C2, and you just start blowing that up, you could just do it explicitly and figure out what the homology class of the disk is you get after you finally smooth that singularity, count up its self-intersection, you've got its surgery coefficient, and it just works. So it's exactly the same as the ceiling of that minimal coefficient that bounds negative definite. And if you're curious, well, from that expression they gave on the previous slide, that's PQ minus just, instead of AN through A1, the AN is like the floor of that thing. So there it is. Okay, so like I was saying, that's telling you that torus knots, for example, always have, as soon as you bound negative definite, you got a fillable at the same time. Okay, so let me go back now to this other order to the proof. So the main theorem was basically this: you have a Legendrian in a contact manifold, asking when there's some positive coefficient that has that's fillable, and you want to show that happens if and only if K bounds a symplectic disk in the filling. So one way to think about it is, well, if you're doing N surgery, there's a two-handle cobordism from one to the other. And it turns out that some work of Chris Wendell, along with sort of massaging your picture a little bit to make sure the theorem applies, shows you that this cobordism between these two three manifolds has the structure of a weak symplectic cobordism, although it goes the other way from Yn back to Y. Okay, so if you have a weak cobordism from Yn to Y, and you have a weak filling of Yn, you can glue those things together. So you put the weak filling onto Yn, then you attach this cobordism back to Y, so that gives you a filling of Y. And the core of that two-handle that we started off with is kind of obviously symplectic in the construction of Wendell, and it bounds the knot. I mean, that's what a surgery cobordism does. It's a disc attached to your knot. That actually, this direction was more or less shown in some earlier work of Boulont's with Jamie Conway and John Detmeyer. So I mentioned that. So for the kind of harder work is going the other way, that if you have a disc in a symplectic filling, boundary is some transverse knot, then you can scoop out that disc in such a way that the complement has, the restricted symplectic structure is a weak filling of some contact structure on the boundary. And in fact, that contact structure is obtained by positive contact surgery along the knot. So that's sort of an analysis of local models and lots of patching things together. And in particular, you end up sort of braiding your knot in some way with respect to an open book, and yeah, just doing some geometry, I guess. So that's that, and I'm going to stop there.
Thank you. Are there questions?
I'll jump in with the question. Overall, really cool, interesting. The examples you mentioned early on where the clasp number is arbitrarily large relative to the genus, is it sort of clear why in those examples they aren't, the surgeries aren't fillable, or they don't bound, some